Hello everyone. For this tutorial video, I like to explain how to compute the definite integral, given that we found the equation for it in the last video, as well as use this equation to prove the properties of simple definite integrals. In particular, we remember that the change of x is given by b minus a divided by number of rectangles. So if we flip the positions of a and b, we also flip the positions in the subtraction. And we can see with some clever foresight that one is simply -1 times the other. And we also see, because we have a negative sign attached to every single term, this means the negative gets multiplied by the entire sum. And lastly, we can factor a negative out of the limit by properties of limits. And we should conclude that when we switch the limits of integration, we get the same general value, the only difference is the sign is negative. The integral from one point to the same exact point is 0 because when we use the definition of change of x, we get 0.1 minus 0.1 divided by number of rectangles equals 0, regardless of the exact number of rectangles. And the sum of anything times 0 is always 0 plus 0 plus 0 plus 0 plus 0, etc., regardless of how many times it is added. So the sum is 0 in total. And the limit as n approaches infinity of 0 is simply 0 because 0 does not depend on n or any variable. We can prove we can factor a constant out of a definite integral by first starting with the definition of the definite integral per usual. So we have constant times the function. We see because the constant is multiplied by the function for every term in the sum, we can factor the constant out of the sum in total. And lastly, we can factor the constant out of the limit by properties of limits. So in conclusion, we can factor a constant out of a definite integral. We can prove that the definite integral of a sum or difference of two functions is exactly equal to the sum or difference of the individual integrals by first doing the usual process of defining the function, which in this case is the sum or difference of two functions. Then we can see by properties of sums we can break this as a sum of two separate functions. And we can also see we distribute the limit by arithmetic and properties of limits. And we conclude that these are two separate definite integrals, that is the sum or difference of the individual functions. We can also prove definite integrals of very, very simple and specific functions. In particular, the definite integral from a to b of a constant is exactly equal to the value of the constant times b minus a, which may seem arbitrary or like it comes out of nowhere, but the proof of it is in that we start at the definition of the definite integral using limits per usual. We use c for f of x because that is what we are given, and we rewrite change in x as b minus a over n, which we will use to cancel out factors as we will see shortly. We see that the result of the sum is c times n because it is c plus c plus c plus c plus c n times. So now we can see that the n's will logically cancel out. And our final answer is that the integral is c times b minus a because at this point none of the variables are affected by n. We can next prove a property of integrals so important it is called the fundamental theorem of calculus because it relates integrals and derivatives specifically. If we first assume that x and x plus h are on the interval from a to b, and we define g of x as the integral from a to x of f of t with respect to t, we would first compute g of x plus h minus g of x using what we have for g, and see with some careful reasoning we can actually rewrite the left-hand part of the computation as the integral from a to x plus the integral from x to x plus h, because of how you can break a definite integral into smaller parts, which should become obvious if you think of it as the area under a curve, and we know from geometry we can dissect an area into smaller areas. So now we see two of the terms cancel out, and if we now divide by h, we have 1 over h multiplied by our result. If we next recall the extreme value theorem, which we proved earlier, we should be able to see that there's an absolute minimum and absolute maximum in the domain specified. So we use the appropriate substitutions and then divide everything by h. And now we can substitute in the derivative for the middle part. However, we do not have concrete evidence yet that we have the derivative because we did not take a limit, but we will do that now. The limit of function of c as h approaches 0 is the same thing as saying limit of function of c as c approaches x because h is a change in x, and this equals function of x. We do the same exact thing for the limit of function of d, and conclude that it is exactly equal to function of x as well. So now we have proved concretely that the derivative is exactly equal to function of x. So we shall now conclude that the derivative of g of x is exactly equal to function of x. And we defined g of x as an integral of f of x in the beginning of the problem. So now we know concretely that if we take the derivative of an integral, it will simply undo the integral and give you the function. There is another part of the fundamental theorem of calculus which is somewhat easier to prove and actually helps you make computing definite integrals much simpler. If we use two functions that are specifically defined as indefinite integrals or antiderivatives and take the difference of these, we would see the constants of integration in the two indefinite integrals cancel each other out. And this should simplify to the definite integral from a to b minus the definite integral from a to a, which is equal to 0. So in conclusion, the definite integral from a to b is the antiderivative of b minus the antiderivative of a, and that's all there is to it. Now that I have successfully shown you all of the properties of definite integrals, I can discuss more thoroughly examples of how to use the last formula to make computing definite integrals of specific functions easier. Don't forget to subscribe if you found this video informative, and make sure to see other tutorial videos, and follow me on either Facebook or Twitter for more content.